Hello everyone and welcome. Today we're diving into some of the most beautiful puzzles light creates all around us every single day. This is a fantastic topic, especially for all you Class 10 students out there getting ready for your exams. Now, before we jump in, a big shout out to A1 Institute for making this possible. If you're looking for top-notch guidance and notes, you can find their contact info right in the description. And hey, if you love this kind of stuff, make sure you like, share, and subscribe to the A1 Institute YouTube channel. All right, let's get started. So let's kick things off by exploring a few mysteries you've probably noticed just by, looking at the world around you. First up, the big one. We see it pretty much every clear day, right? But what's actually going on up there? What's the physics that paints our whole sky that incredible shade of blue? And building on that, why does that same sky put on a completely different show at sunrise and sunset? Where do all those amazing reds, oranges, and pinks come from?
And then there's a nighttime puzzle. You look up at the night sky, and you see the stars flickering, kind of dancing around. But planets, like Venus or Jupiter, they just shine with this really calm, steady light. What's the deal with that? It all comes down to the behavior of light.
To crack these puzzles, we need our first key. And believe it or not, it has to do with the secret that's hidden inside plain old sunlight. Okay, so our first big idea is called dispersion. It sounds a little technical, but it's actually a really simple idea. It's just the process of taking what we see as white light and splitting it apart into a whole spectrum of individual colors. And a simple glass prism is the perfect tool for this. It's like a light sorter. When white light goes in one side, the prism bends each color just a little bit differently, fanning them all out so we can see them one by one. And here's what's so cool. The order of the colors is always exactly the same. It starts with violet, which gets bent the most, and goes all the way to red, which gets bent the least. This is that classic rainbow spectrum that we all know and love. Okay, that's great for a little glass block in a science lab, but how do we get from that to the gigantic, beautiful arc of color we see stretching across the sky? Well, the answer is actually pretty amazing. After it rains, the air is filled with millions and millions of tiny little water droplets just hanging there. And each and every one of those droplets acts like a miniature prism. It takes in sunlight, splits it apart, and sends out a tiny little rainbow. When you put them all together, you get the huge one we see. All right, let's move on to our next clue. For this one, you have to imagine our entire atmosphere as a giant, invisible, and constantly moving lens. This phenomenon is called atmospheric refraction. You see, as light travels from the vacuum of space into our atmosphere, it has to pass through all these layers of air that have different temperatures and densities. All those changes cause the light's path to literally bend. And this is exactly why stars twinkle. Starlight travels an unbelievable distance to get to us, so it arrives as a single tiny point of light. As that little point of light zips through our constantly churning, turbulent atmosphere, its path gets bent back and forth really, really fast. And what we see down on the ground is a star that seems to flicker and shimmer. So why don't planets twinkle? Well, it's because they're so much closer to us. They aren't just single points of light. They actually appear as tiny little disks. You can think of a planet's light not as one ray, but as a whole bundle of light rays. And while each individual ray is getting jiggled around, the overall effect just gets averaged out, giving us that steady, unwavering glow. But atmospheric refraction does more than just make stars twinkle. Get this, it actually plays a trick on us every single sunrise and sunset. Because it bends light downwards over the curve of the Earth, we can actually see the sun's image appear above the horizon before the sun has physically even risen. And the exact same thing happens in reverse at sunset. So how much of a difference does this really make? In total, this effect gives us about 2 extra minutes of daylight every single day. It's like a little gift from the physics of our atmosphere.
And now for our final piece of the puzzle. This is the one that's going to solve the mystery of our blue sky and those fiery red sunsets.
This next idea is called the scattering of light. So when sunlight comes into our atmosphere and hits all the tiny molecules of gas and dust, it doesn't just pass straight through. Instead, it gets absorbed and then shot back out in all different directions. You can almost picture it like light is playing a giant game of pinball with air molecules. Okay, so here's the key to the blue sky. The tiny molecules in our air, mostly nitrogen and oxygen, just happen to be the perfect size to be really good at scattering light with short wavelengths. And guess which color has a short wavelength? Blue.
So as sunlight streams in, the blue part of it gets scattered all over the place. No matter where you look in the sky, you're seeing all this scattered blue light coming at you, making the whole thing look blue.
But this whole picture changes completely when the sun is low on the horizon, either at the very beginning or the very end of the day.
Think about it. During a sunset, the sun's light has to travel through a much thicker slice of the atmosphere to get to where you're standing. Along that super long journey, almost all of the blue light gets scattered away from your line of sight. So what's left over? Only the longer wavelengths, the reds, the oranges, and the yellows. That's the light that makes it all the way to your eyes, creating those spectacular colors we love.
So let's just take a second and bring this all together and see how these simple principles of physics totally re-illuminate the world we see every day.
It really just comes down to these three simple actions. Refraction bends light, and that gives us twinkling stars and a little bit of extra daylight. Dispersion splits light, which creates rainbows out of raindrops. And scattering bounces light, which is what paints our daytime sky blue and our sunsets red. Bend, split, and bounce. That's the magic.
And that last point really shows how much our view of the world is shaped by these basic rules. So here's a final thought I want to leave you with. Imagine you're on another planet, where the atmosphere has bigger particles that are really good at scattering red light. What color would their midday sky be? And what amazing colors would paint their horizon when their star sets? It kind of makes you see our own sky in a whole new light, doesn't it? Well, that's all for today. Don't forget, for admission or notes, be sure to contact A1 Institute. The number is in the description below. Thanks for watching.